Here's a video showing how the length of a MOSFET can affect the threshold voltage. So right here we've got an NMOS setup. It's diode connected. We're going to sweep the drain voltage and just measure the current. If you click in, you can see that I've set the model name to the AMI now on semi half micron process, and I'm programming the channel length and the channel width. Right, I've set the width to 3 microns. I just happen to know that when the width is 3 microns, that'll mean that there's at least 2 contacts points into the drain and the source. I'm going to step the channel length from the minimum drawn length of 0.6 microns up to 2, stepping it by 0.1, and then we'll sweep the input voltage from 0 to 5. We'll let that run. So in a classic N MOSFET model, we should get 0 current and then something squared, right? So that to obey the square law. Well, that's not exactly true. So if I plot this on the log axis, you'll see that between a certain range, I'm actually getting a linear plot, and that's because in subthresholds, MOSFETs have an exponential current relationship. Important thing to look at is that the slope is the same, and yes, as the channel length increases, the current gets smaller, but as you would expect. But notice it's kind of taking longer and longer to turn on. And that's because the threshold voltage is changing. Now it's a little hard to see from that plot. All right. But if I just take the square root of this, right, I should get a straight line wherever I'm getting a squared dependence. And you can see that we don't, and that's okay. But there's regions where it is straight-ish. And if I take this point and then take the tangent of it and see where it hits the x-axis, that's kind of my threshold voltage. So if I'm, right in here, it's, like I say, straight-ish. And then if I just draw a line by eye here, we'll see that the threshold voltage is about 0.6 volts. And then as the channel length increases, yes, we're getting less current. But in this straightish era, I draw it back, you'll see the threshold voltage increasing. All right. And so even if we just define the threshold voltage as some small thing, you can see that these are turning on later and later as we sweep the voltage. All right. So if we want to know what the threshold voltage should be, well, we just look at the SPICE deck and it's 0.6 volts. But that's like for the minimum channel length. This gets modified by these parameters. I'm not going to go into it now. All right. Now the thing is you'd like to know, what we want to know is what channel length will what's the minimum channel length for which it'll stabilize. All right. Now to do an automatic extraction where essentially I'm saying find where it looks like a straight line and extract from there. Well, you can see that range changes wherever you go. So this is actually a hard way to do it. Another way is we bias it in the triode region, So we set the drain to source voltage to some small value, right? And then we sweep VG, and we get a slightly different curve. Now, there's a different way to analyze this, is that you take the derivative. Now it's easy to see that there's a maximum in that, and this is GM, by the way. The derivative of the current versus VG is GM. So you can see there's a clear maximum point. And what we do algorithmically is I find this maximum point, and then on the ID curve, I just find the tangent, and then find where the tangent of that line hits the x-axis, and that gives me the threshold voltage. Now this threshold voltage will be a little bit bigger than the other one because the drain to source voltage is kind of small, and we're not getting channel width modulation, excuse me. So if we look, I actually have some code here where you measure, find Gmax, right, where the derivative of the drain current is maximum, then find the y-axis point at that point, right, find ID max, where the current, which is ID when we're at Gmax, and then find this gate voltage when this happens, right? So the beauty of that is that when I run that simulation, it's extracted all these numbers for me. All I have to do is plot stepped measured data, and there's my values. All right. Now you can actually program right from here the threshold voltage. All right. And it's really, this is just the x-intercept equation. All right. And you can see that at half a micron, the threshold voltage is 0.9. And the reason is that the drain to source voltage is just a lot smaller than in the other simulation, where they're both, the drain to source and gate to source are equal and changing. But I could try to take the derivative of this, right? And at first it's changed, the threshold voltage is changing a lot. These kind of steps are because there's just not as many steps. There's only 15 simulation steps, right? So here, if I go from half a micron to 0.7, yeah, there's a big change in threshold voltage. And as we get down to 2 microns, it's smaller, right? So if I wanted to it'll just take longer if I keep that up. So if I wanted to have more data points, I would step it by, you know, half the step that I was doing, and I'd want to try a longer channel length. So that was 69. So again, what we do is we'll view the SPICE error log, plot step measure, data, that's GM max, right? See, it's a lot smoother. And then I'm just going to steal this code, which you could program as well. it's not quite, because that goes to 4 microns. Okay. So when the channel length is small, changing the channel length by a little bit affects the threshold by quite a lot. But when we get down to, or up to 4 microns, right, the change is a lot less. It's not insignificant, right? Um, but it is something to look at. Again, let's just look at the threshold voltage again. And you can see that it starts here, right? And it changes a lot, and then the change starts to even off. Now you might say, why is it changing? Well, there's process variations. So you might draw 0.6 microns, but it might be a little bit bigger and it might be a little bit smaller, and it might behave in some variable way. So remember those current mirrors, right? It relies on the transistors matching, right? That means that the length is the same, the width is the same, the threshold voltage is the same. All these parameters, right, which are extracted really for just one transistor, they all vary statistically, right? So if we want good matching, right, yeah, we could use 4 microns. Now, let's take it even farther. Okay. Sometimes for analog devices where you need high gain and stability, we can go to 10 microns. And I guess that's 189 runs. These files are on Canvas, by the way. That was probably longer than we needed. Alrighty. Again, view error log, plot step data. There's the derivative of it. Right. I don't know, let's even take it on a log scale, see what happens. So it never goes to 0, but the effects get small. Right. Now the thing is when transistors are close by, I mean, if you draw 0.6 microns, you're not going to get, 0.6 or 1.5. No, there's a percentage around each area. So if I varied by 5% here, you'd see how the threshold voltage would swing back and forth a lot. If I went 10% back and forth here, right, I mean, the threshold voltage almost looks constant. All right. So the thing is for our design, do we need like perfect matching or really trying to make it smaller, right? A longer channel length will help with the DC gain, all right? But so that's something that you guys can do. Extract, do this Same setup, but for the PMOS. And all you'd have to do for the PMOS is add where is it? PMOS 4, right? Here, the model name, right? Here was AMI 05N. Here it's AMI 05P, but you can set LP and with WP, right? Now again, the PMOS, you have to bias it what you might call backwards, and the currents can come out negative. So sometimes you, in order for this analysis to work, you've got to take the absolute value of things. Oops, I should have put P. Yeah. I'll get the TSMC 0.18 as well. But that would be the first step. Because once you set that channel length, then everything kind of just goes off of that, right? That's the channel length of your differential pair. That's the channel length of your current mirrors. That's the channel length of the beta multiplier. But really understanding how that channel length variation affects something just as simple as the threshold voltage and how that can cause offsets is something that you can explore in LTspice. Although I don't know where it went. Getting pretty close with the cadence. But really, the cadence will use this same file, right? The difference is cadence will automatically calculate some of these things for you. Right now, you'd have to enter in your own equation for the areas, and without that, the capacitance data doesn't mean anything. But anyway, you can download a sample file of this one and this one, and you can explore that for the next time.